Okay, it's an excellent alternative. I mean, it's under that physical vapor deposition, but whatever PVD, so this is actually vapor deposition method, but this is a little bit different. So instead of using heat to eject the material from the source, in physical vapor deposition, there is a heat source is there. So that is in, but in case we can bombard them with high speed of particle. So let's understand the sputtering process once again. In sputtering process, what is happening? This is substrate holder, and on top of that, this is a substrate where that you have to do the deposition, and this is target. Okay, so target site actually this means whatever material you want to deposit, let's say Al2O3 you want to deposit. So Al2O3 should be in that blue color, that is material. And then argon gas, you need to have a vacuum in the chamber, but not that high vacuum. Then argon need to be purged. Then some voltage need to be applied and plasma will generate. And when plasma will generate, then argon plus charge actually will start bombarding on this surface. And here you can see that incident argon atom, when it's hitting on the target, then during ejection that it's actually emitted, the target atom actually it's actually coming out from this surface. So this is actually, you can see that emitted target atom. Okay, so target atom is actually basically coming out. Okay, and this is happening, and this emitted target atom basically is actually, it will be deposited on the substrate, and finally you will get a film on the substrate. So same thing actually here, this is actually better this clarity. So there is a gas chamber, and this is a sputtering unit, and this is actually the target. So DC or RF supply need to be there, and this is the substrate. On the substrate you have to deposit, and this is the plasma generation. And during this sputtering process, from that window you can observe there is a color of the plasma. Let's say that if you are going for, whenever you will be going for scanning electron microscopy, please observe this one, that a gold coating unit. There you can observe some pink color plasma generation. Okay, and of course that there is also, you need a shutter. So this shutter and then like actually will help you to get that proper deposition and other thing. So that means that instead that using heat, here what we are doing, by using the charge particle bombardment of the surface, and that source atom will be ejected. The momentum transfer from the particle to the surface atom can impact enough energy to allow the surface atom to escape. So that is actually happening. So that means this particle or charge argon particle should have sufficient energy, then only it can do the bombardment on the surface. As for example, let's say Al2O3 source or Al2O3 target. So aluminium and oxygen need to be sputtered by this argon plus. So that means argon plus should have sufficient energy. It should break the bond between this, I mean, aluminium and oxygen in the lattice or from the surface atom. And surface atom, you know that energy will be little bit less compared to the bulk. So that means that it will be little bit easier that to remove this surface atom. Once ejected, those atoms can travel to the substrate and deposit as a film. So this one, that ejected atom from the source, it will deposit on the substrate. And there are several considerations here: creating, controlling, and directioning a high-speed particle stream. So creating, controlling, and directioning a high-speed particle stream, that is actually very much important. An interaction of this particle with source surface and emission yield. So first actually that you need to generate this argon plus, and then how from argon to argon plus formation will be there, I'll explain. Second, argon plus need to interact with the source. Let's say as for example Al2O3. So on Al2O3 surface it need to have interaction, the deposition of that emitted atom on the substrate and film quality. Then emitted aluminium and oxygen will deposit on the substrate, And then quality of the film, you can again that you can do some substrate temperature and other thing to get that quality of this film. Like in PVD, that we observe the temperature and the deposition rate, substrate temperature and the deposition rate. These are actually two important factors is deciding this quality of the film. So atomic particle can best be easily controlled by electromagnetic methods if they are charged. A weakly charged gas or particles that exhibit collective behavior is called plasma. So in this particular sputtering, when you applied that bias, there will be first actually that plasma generation will be there. And argon need to convert to argon plus. Then the source material is called target, and that emitted atom or molecules are said to be sputtered off. So source in PVD, source actually whatever that will be melt and then evaporated one will deposit. But in this case, source is target, and from the target that atom or molecule will be sputtered off. So now in this, the sputtering process, and this sputtering, why am I explaining in details? This is a very important method and you need to know, because sputtering, wherever you will go, you should have the sputtering. It could be industry, it could be, I mean, like academic, like everywhere that you have to deal sometimes with sputtering. So in sputtering, the target materials and the substrate placed in a vacuum. So that is actually basic requirement. So this is actually target cathode and this is the substrate. Voltage is applied between them so that target is the cathode and substrate attached to that anode. Now in plasma is created by ionizing a sputtering gas. So sputtering gas means actually some inert gas need to be purged into the chamber, and generally a chemically inert heavy gas like argon. Then sputtering gas bombards the target and sputtered off the material we'd like to deposit. Okay, so the sputtering gas bombard the target and sputtered off the material whatever you would like to deposit. Now this creating and this controlling of the plasma, how this actually plasma formation is there. So ion can be generated by the collision of the neutral atom with high energy electron. So neutral atom and this high energy electron. Due to this collision, you can see that E minus and this argon, 2 electron, and then again this argon plus. Argon will convert to argon plus. Why it's become 2 minus? Because this argon, when it's converted to argon plus, one outer cell electron will be coming out, and those electron, these 2 electron, again can convert new argon to argon plus. So that's why this is a cascading process. It's going on. So the interaction of this ion and the target atom, the targets are determined by the velocity and the energy of this ion. So after ion formation, then ion actually will interact, and that will be decided by how that energy of this ions. This interaction, according to that interaction, because this interaction energy, that is also in some slide actually I'll explain. Then in which energy of the interaction the sputtering will happen. Since the ions are charged particle, electric and magnetic field can control this parameter. Okay, so when ion is charged, it's much easier by electric or by magnetic field, it can be controlled. The process begins with a stray electron near to the cathode is accelerated towards the anode and that collides with a neutral gas atom and converting it to a positively charged ion. That is actually a normal process. At the beginning also I told the process result into 2 electron which then can collide again to fresh argon, and then actually it will it's form actually series of argon plus. So this cascading process until gas breaks down. Okay, until gas breaks down means you will get a maximum number of argon plus. So breakdown voltage depends on that pressure in the chamber and the distance between anode and cathode. So you have to reach this breakdown voltage, and that depends on pressure in the chamber and distance between that anode and cathode. Now question is that how to control the pressure? Like first you are getting a vacuum, then control way you need to purge that argon. Okay, if you purge too much, then what will happen? The pressure will high. At very low pressure, so there are not enough collision between atoms and the electron to sustain a plasma. So if you go, just remember, in case of physical vapor deposition, we went for a very high vacuum. And in that case, what will happen? That mean free path increase like anything. But that is we don't want in this case. Okay. At too high pressure, there are so many collision between the electron. So electron will lose their energy. So electron will not have sufficient energy to transfer to this argon. So that argon will convert to argon plus. So that is also problem. So that's why pressure should be balanced. And in this diagram, you can see the breakdown voltage and this is the chamber pressure. So in a particular that pressure that you are getting actually this that how it's actually changing with this pressure. So this is actually optimum pressure, and this is this there actually you are getting breakdown voltage at lower actually very low value of um, um, electric potential. So now another is the glow discharge formation. What is glow discharge formation? As I told that if you observe during the sputtering process from the window, always you can see that there is some color formation. So people when use that sputtering, they observe that color is coming or not. If color is coming means your plasma generation started or sputtering started. So why this color? So some of this electron atom collision will produce light instead of electron and atom instead of electron and ion, and the plasma will glow accompanied by a voltage drop. Okay, so that is actually happening. So now this is actually the glow discharge. What will happen? This is anode and this is this cathode. So on top of cathode, the substrate is placed. So this is actually very near place, but in the schematic, it looks it's far, it's not that far. And this is the anode. So you can see this side actually you have to do the deposition. And this region should be in negative glow region. Okay. So where actually this deposition is happening. And then positive glow region here. So this is also this positive glow region. You can observe from your bare eye that this color. This is called the positive glow region. So different name is there like anode, dark space. You need not to understand this exact whatever these regions are there. Just keep in your mind that this is positive glow and this is the negative glow. So positive glow there it will be visible from the window of this particular sputtering. Main plasma region, this is uniform field strength and equal number of electron and ions, more or less. This positive glow and the negative glow, what is that one? Due to reduced density of the electric field strength become weak. Electron have the right energy to cause excitation. Okay. So this is actually these 2 point is very important, and other like astrom dark space, space, then cathode glow, and then cathode dark space. So these are different regions are there. So we are mostly interested of these two. Okay. And these two region actually, and substrate should be placed in this negative glow region. So that means this distance cathode in between cathode and anode, we should not change arbitrarily. It should be a optimized distance. As I told, that collision, this is here, this line is very important, the breakdown voltage. What is the breakdown voltage? This is actually from ion to atom to ion formation. Okay. And that is actually this breakdown voltage depends on the pressure in between the chamber and distance between the anode and cathode. So these two factors is important. That's why in particular sputtering, chamber pressure is extremely important. If you change the pressure, so people what they will to do, like changing the pressure and measure the quality of the film, and it's highly dependent on this particular chamber pressure. Okay. And another is actually cathode anode distance. So cathode anode distance, you don't have the liberty to change. So like if you purchase one instrument, there will be a fixed distance between the cathode and anode. So this plasma pressure, so as I told that unless there are enough collision, the plasma will quickly die. So that means continuous that electron and argon atom, that collision is required. Then only that plasma will sustain. That cascading process should continue. In order to have a self-sustaining plasma, each electron has to generate enough secondary emission. So what is the secondary emission? This is primary electron and this is secondary emission. Okay. So after collision, you can see the two electron formation is there. So this process should continue. Then only you can sustain this plasma formation. And since we want collision to occur, so the pressure cannot be too low. The mean free path should be a tenth or less than the typical size of the chamber. So mean free path should be less than the chamber length. Now, what was the mean free path in physical vapor deposition? Can anyone tell approximately? Mean free path in physical vapor deposition? Can anyone tell mean free path? Anyone? Mean free path in physical vapor deposition? No one? Why?
Around 1 meter.
Around 1 meter. Yeah. Okay. That makes sense. Okay. But I mean more than 1 meter is also is there. According to if you go for vacuum. If you increase the vacuum, distance will increase. Okay. It can reach to kilometer also sometimes. Okay. But in this case, it will be lesser than typical size of the chamber. So that means you can correlate vacuum requirement is much lesser in case of sputtering compared to physical vapor deposition. So since we want electron to gain enough energy between the collision, pressure cannot be too high. So we should not go for means near near atmosphere pressure. Its sputtering will not possible because this atom means there will be a huge collision between electron itself. And this mean discharge tube pressure around 10 to 1000 milliliter, and then plasma density around 10 to the power 10 to the power 12 parts cm cube. And plasma density means this is actually whatever the particle contain the plasma, material contain the plasma. Like plasma consists of last class I explained positive charge ion, then electron, free electron, the neutral atom. These are actually things mostly there in this plasma, and sometimes some unreacted, I mean atoms. So now this ion surface interaction. So in ion surface interaction, what is happening when ion bombard a surface? Several things can happen: reflection, sticking, sputtering, ion implantation, chemical reaction, electron and photon emission. Okay. And this ion beam energy is that critical parameter. So in sputtering, 3 to 10 kilo electron volt is required for the sputtering. But if you see less than 5 electron volt, adsorption or the reflection 5 to 10, surface damage, migration, greater than 10, ion implantation. Okay, so in 3 to 10 we are getting this sputtering process. Now this how ions sputtered atom. So when ions actually collide with the surface atom on the target. So surface atom on the target. So on the target surface, whatever atoms are there, those will actually first hitting will be on those atom. The energy transfer can knock some of these atom off the surface. And as I told, surface atom energy will be slightly less because surface has a broken bond. So the key principle is that energy and momentum conservation, and any collision the momentum is conserved, and if this collision is elastic, kinetic energy is also conserved. Okay, so whatever that collision is happening, that is actually we need to understand if the collision is elastic, then kinetic energy is also conserved, and this energy is required for sputtering are much higher than this lattice bonding or the vibrational energy which are cause an inelastic vibration interaction. Therefore, sputtering condition can be considered elastic. So this is very important. In sputtering, whatever collision is happening, sputtering process, that is actually elastic collision. Okay. And this energy, whatever the required energy, should be higher than that lattice bond energy. So here you can see what is happening. So momentum and energy, maybe actually next class I will explain this part, and this entire slide actually I will put it in this Moodle, and last previous part also I didn't put it. So some basic question from this sputtering you can expect in your quiz, and I want to take another one class. So I request the seer, can you please add and give some other timing for the presentation? Seer? Seer, can you hear me? Seer is not there. Okay, I'll speak to him later. Okay, then I'll just another one slide, I'll finish it and then. So momentum and energy transfer, what is happening that M1 V1 and this is M2 V2. So this is argon and this is actually that whatever that target atom. So then what is happening M1 V1, and in this case actually M2 V2. So this momentum P is equal to mv and kinetic energy half mv square. So P initial that M1, this V I1 M2 V I1 and equal to this one. So this is M1 Vi1F M2 V2F. Then Pf final M1 V1F by M2 V2F. Okay. And K1 is half mv square, that is actually terminology, and K final half mv square again. So from this actually that momentum, this maximum energy transfer in such a collision occur when these masses are equal. So in that case actually it is happening. So that this is actually it's a collision, and if angle formation is theta, so K2 by K1, this 4 M1 M2 by M1 plus M2 square cos square theta. Okay, so this is actually K2 and this is K1 and this is K2. So this kinetic energy before collision and this after collision, that whatever that kinetic energy, and that is actually with this one and K1 by K2, we can actually calculate that initial by the final, and this with changing that M1 by M2, that this one also kinetic energy also changing. So that means, and as he told, the maximum energy transfer when that masses are equal. So masses are equal means argon plus that is hitting on the surface. So surface atom mass are equal to this, I mean whatever this argon plus atom. So this is actually the curve. So with that increasing K1, this actually K1 by K2. So K1 actually that initial energy and Kf is that final energy. So K2 is the final energy. So K1 by K2, you can see that this is increasing gradually with M1, M2. And then M1 by M2, so when it will be equal to 1, so you can get that K1 by K2, that is also 1. So what does it mean? Like actually this kinetic energy actually of this like actually K1 and K2 part, it will be equal. Okay, so maximum energy transfer in such a collision when masses are equal. So masses are equal, then actually maximum energy transfer is happening. So this is actually this from this K1 equal to K initial equal to K final, and this is P1 equal to this P final. If we consider that energy transfer is 100%. Okay, so because in 100% energy transfer case, it will be like this. So direction of this emission for a normal incident of this ion, the primary collision cannot eject an atom off the surface, and however the secondary collision can. So what will happen that sometimes actually this, I mean for normal incident ion, primary collision cannot eject an atom on the surface, but secondary collision, you can see that this incident atom will hit on the surface. This one further it will hit the next atom, then hitting the next atom, and finally this another one atom will grow from the top. It will go from the top, and apparently we might see that okay from the top it's actually going out, but is actually secondary due to the secondary collision. Okay, and primary collision can result in actually ejection, the thing, the billiard ball. Okay, so I just finish it here itself. Next class again I'll continue, and I'll talk to yours here, so that this exam timing, if we can arrange some other timing, at least I can have a one class. Means quiz actually if we do in some other time, so I can have a class. Utsav, you are there? Okay, so he is not there, so no problem. So I have taken the attendance. Okay, thank you. Then this Thursday, actually, I'll talk to him. Some other time, actually, quiz will be there, one small quiz. And this I'll have my regular class that is in regular timing. Okay, thank you. And I'll, whatever the some pending class notes as well as video is there, by today only I'll put everything in that Moodle. Okay, okay, bye. Thank you.
Thank you, sir.
So one question is there. So just actually, I mean, you can other can move. So I like actually this question. Electron collide with argon to make argon plus, then argon plus hit the target, and then metal come out. But metal is going towards, when metal is going towards the substrate, what if Al become Al3 plus, that because of the collision from this electron? Yeah, that is a very good question. So this is actually, I mean, it's a lighter particle, so that will actually aluminum, and this is actually some, there is some chances there, it may happen, but electron actually, I mean this argon, some of the argon may aluminum may convert to Al3 plus, but most of the cases, this aluminum actually will have a sufficient energy. It will actually, although it need to cross the region of plasma, but easily it can it can reach. Majority of the aluminum can go in the form of aluminum only up to the substrate. But this will happen. Some of the aluminum may happen. That is correct. It's a good question. But majority of the aluminum atom, sputtered atom, will reach to the substrate. Okay. So that is a good question. Thanks for asking this question. It's clear, Nitin?
Yes, sir. Yes, sir. Clear.
Yeah. Okay. Okay then. Bye.
Thank you, sir.
Thank you, sir.